Hello, Satya. So today we are with another problem of CSS graph sheet, which is a massive root problem. This is more likely to the developed problem which we solved earlier. So first visit that video and solve this problem. Solve that problem, then come on that problem. Okay. So in this problem, this results network has n computer and m connection, and your task is to find whether we can send message to Mazars, and if it is possible, then what is the minimum number of computers on such a route? Okay. In the input section, it is given that Ulobi computer is 1 and the Mazars computer is n. So what we have to find? We have to find whether it is possible to go from computer number 1 to computer number n. If it is possible, then we have to print the number of computers on that route, and we have to also print the computer's number. Okay, if it is not possible, just simply print impossible. And another information is given that there is a connection between those computers. Okay, and so there will be at most one connection between any two computer. It means there is no any repeated case. Okay, and the connection will be like undirected graph. It means bidirectional. We can go from computer 1 to computer 2 or computer 2 to computer 1. Okay. So what do you think about this problem? How will you approach this problem? Just think for a 1 minute and then come on the solution. Okay. So let's see about the solution. First, we are writing our basic code, and as there is a one test case, in, so we will take as a t is equal to 1, and what are given as the input n and m. Okay, so in n and m, we will take it as a input, and then we'll take input to our computer connection. So vector vector connection, and there are m connection. Okay, we will take its size as m, computer number m, and the connection is bidirectional, so we will push connection of a dot push back b, and connection of b dot push back a. Okay, right. Now what do you think how we solve? We can solve it by the BFS approach or the digit cross algorithm. But as you can see that for going from one computer to another computer, the weight is always one as there is a connection. So the cost is always one from going to one computer to another computer if there is a connection between them. So it is like a unweighted graph, or the graph have the edges have equal weight. So in this type of problem, you know that BFS is faster, so we will use BFS here. Okay, so first we need a source, but it is given that for that we are applying BFS for solve this problem. We will pass our connection and and, and okay, our dimension. Now we'll make this function. Don't need to here things because all the things that one in our BFS function. We'll take it as a void, and we'll take it as a memory address, my reference and then take the dimension. Okay. Now we need a source for it. So our source is as you can see, like our source is computer number one. Okay, and our destination is computer number n. So int source is equal to one, and int destination is equal to n, and we'll take as a q. Okay, but here we will take pair of intent because we also need to store the cost, and we'll take the cost vector or the count computer, which will store the number of minimum number of computers that are on a root. Okay, int max, and initially we'll take that as a int max, or because we can assume that there are many computers on this row and we have to minimize it. Okay, so we will push first the 0 and the 1, because 1 is our source, and from for reaching from 1 to 1 there is a no there is only single computer, so we'll input 1 and update our own computer with the 1. Okay, it will be about just 1 as there are 10 computers and each of them is in. Okay, right? So then, okay, now what we will do, we will just simply apply the BFS and use the formula that if we are on the current cluster, let's we are on the 10th computer, and we can go from C1 to C2 only if the cost of going from C1 to C2 is less than the overall cost of going to C2 from any other company. I mean to say, if there are two or four possible routes to go from 1 to C2, from source computer to C2. It can be possible by, let's say, we are going from source to C5, then C2, source to C4, then C2. So there are many possible routes can be possible, but we are updating. Let's we are we are currently standing at C4, so we only update the C2. If it the cost of going from C4 to C2 is less than going cost present cost of reaching to C2. Okay. When I will code, you can get the clearly understanding about it. What will I say? So while not q will q dot empty, we will pop the first element of the first computer. Okay. So in current cost is equal to our IT of 0, means current computer is equal to our IT of 1. So it will pair IT dot first and IT dot second. Okay, it will be IT dot second, and now we are iterating in the connection of current computer. So CMC. Okay, if uh, count computers, or it is the cost, you can say it also as cost. So if count computers to reach at CMC is greater than count computers to reach at current computer plus 1, then we will update it. Count computer of CMP will be equal to count computer of current computer plus 1. Okay, and we'll push into the queue. It will get count computer of current computer plus 1, post of what computer and computer. Okay, so it will give the minimum cost or minimum number of computers that can be possible on the root that are starting from the node 1 to that node. Okay, that are starting from to the computer 1. I mean to say that ARM computer will store the minimum number of computers required to reach to that computer from the computer number 1. Okay, so we will get it and it will be perfect. Just simply I print the number of computers required to reach and okay, and will we run on the sample test case right and what we will see. Yeah, perfect. We need three computers. Now we have to also print the root or the computers that are on the root. So what we will see, what we will do, as you know about the Leibniz problem, which I said earlier that first visit that problem. So what we will do in that problem, we will take as a another vector named as parent, which will store that from which computer we have come on that computer. Okay, so let me parent of n plus 1. Okay, now it will store that parent of this computer is equal to current computer. It means to say that for reaching to this computer, let's say this computer is C1. So we are going from C2 to C1. So parent of C1 will store the C2 or the parent of C1. Okay. So now what happens? First we have to check whether it is possible to reach on that computer or not. So if we will check if parent of n minus 1, n is equal to minus 1. It means we can't reach at that point. So we will just simply print impossible. Let me see the format impossible. Okay. And we will return from A. Otherwise, count computers and while parent of n is not equal to minus 1, we will store it in the vector in the computer in route in root parent and this of n is equal to parent of okay. Then we'll push computer in route dot push back 1 because from 1 we are starting and then reverse it or we will reverse it from the back 1. Okay. This is what just print 1. Not the thing. Okay, it will be not split by the perfect. So as you can see, from 1 to 4, we can go from 1 to 4 and then 4 to 5. So that's basically run on the perfectly run on our sample test cases. Now just check on the problem. It is our message code problem and submit it. Okay, perfect. So thank you. If you like the content, so please like the video, comment on the video, and subscribe our channel. That's all for